Time for another design review. This time thanks to Lucas for sending in his smartReflow design, which is a reflow oven controller based on an STM32WB, so wireless and Bluetooth capable IC or microcontroller. It has various interfacing ICs, USB, we have this chip antenna on the PCB, and so on. So thanks for sending in the design, Lucas, and let's see what we can find in your design. If you'd like to have your design reviewed in a future video, I'm trying to do about one design review a month, please go to my webpage at fils-lab.net/contact, fill in the form or just send me an email, but please attach files via WeTransfer or a similar service, not directly. Thank you very much to Altium for sponsoring this video. If you'd like to give Altium Designer a try for yourself, please check out the link in the description below or go to altium.com/yt/filslab to get yourself an Altium Designer free trial. If you haven't tried out Altium Designer before, I can highly recommend using the free trial along with this STM32 PCB design complete walkthrough video, which is video number 41 on my channel, which guides you from project creation all the way to getting your PCB manufactured. In addition, I'm also happy to announce that I'm making videos for Altium Academy, so for more PCB design content, make sure to subscribe to their channel as well. I've briefly looked over the design before, so it's not entirely new to me, but I haven't gone into any great details, so we're going to be exploring this design together. I really liked the structure of his Git repo, with firmware, the MATLAB stuff, PCB, pictures, datasheets, and so on. So that's nicely laid out. We also have a description, in case you're interested. I won't be going into too much detail, and pictures of the assembled board, which happens to be made by GLC. Go to the results, looks like something is working, which is great. And it looks like he maybe hand soldered the QFN, maybe the other stuff as well, I'm not sure. And then we have some to-dos or maybe stuff that does or doesn't work. So Bluetooth works, so that's a good sign. Something with the antenna seems about right. Some other small things. So let's open the KiCad project and start with the schematic. The schematic is a single page, and already I'm quite overwhelmed of how much stuff is on a single page. So initially my first thought is, okay, yeah, it's nice that you can fit it on one page, but it doesn't mean you have to. It would be nice to have this in sections, maybe a power section, maybe a microcontroller section, RF section, and so on. Another thing I noticed straight away that even though it's sectioned, that it's not sectioned logically. We have some part of the microcontroller up here, and then we have another part of the microcontroller on the right. We have part of the microcontroller on the bottom left. So that to me doesn't make much sense. I would like the microcontroller parts all grouped together. It might be nice that this part is segmented, so you have a boot and oscillator section, and you have a power section, and you have a general purpose I/O section, but still I would recommend putting that on one page, grouping that together, rather than having to jump around the schematic. Because in this way it looks like these aren't related, but they are. As usual with these design reviews, this isn't a particularly formal design review, I'm just going and jumping through, picking out things that immediately jump to my attention. I'm just going to start at the top left and work my way through the schematic before we look at the PCB design. Power-wise, it's first of all unclear how this is powered just from looking at the schematic. It turns out that this is actually simply powered via this header connector over here, but it looks like the USB V-bus pins of this connector, and there's also a second USB connector down here, are being used or at least tied to the ESD protection, but it doesn't seem like on the schematic that it's being used anywhere else. So I'm just going to assume we're just going to be powering it through this J11 header. If you were going to power via USB-C, you can see these CC1 and CC2 pins, basically the communication channel pins, would have to be pulled down with 5.1 kilo ohm resistors on each of those lines to be able to extract, so to speak, power from USB-C connectors. So this is another hint that we're not using power. Mounting holes are connected to ground, and I would probably advise against that for this kind of device configuration. If we're using a conductive enclosure, there's different rules we have to go by, but generally I would leave these mounting hole pins floating. If it's not going to be an enclosure, it's going to be a plastic enclosure, and if it's not a host. I like the little layout guidelines that we want to route than the USB at 90 ohms differential, so I like that there's some comments sprinkled throughout this design. Then we have the microcontroller, which is an STM32WB. Now Lucas hasn't filled in the XX, and that would be nice to know what specific microcontroller this is, because that lets you verify the pinout, the datasheets, and so on. But let's assume all the pinouts are correct. I won't check this, so we have serial wire debug, UARTs, USBs, SPIs, and so on. And the first thing I know to notice here, we have one of these WS2812 RGB LEDs, which are very common. You need a data signal from a microcontroller and then apply power to this IC pretty much. That's what it is. It has an internal controller, and then you can program it to do any sort of RGB color. However, there's a catch with these. First of all, they run from 5 volts power, but I don't think they are compatible with 3.3 volts. So I've opened up a WS2812B datasheet, We have absolute maximum rating, so you can power it from between 3.5 to 5.3, but I believe nominal is 5 volts, so you can't power this from 2.3 volts. Since Lucas is also powering us from 5 volts, we have to look at our input high and input low voltage levels, which we can find in this table. So let me zoom in a bit. Input high is 0.7 VDD, and VDD is 5 volts, so input high is 3.5 volts. So our microcontroller runs off 3.3 volts, therefore it will not recognize this as a high. So this LED won't be able to be addressed. And this is actually quite a common mistake. I've seen that quite a lot before, that people try to use these LEDs but don't realize that it hasn't got typical microcontroller interface logic. Either need a level shifter or you need to choose a different LED. Also, I'd like to see at least 100 nanofarads decoupling between power and ground of this RGB LED because it is an IC. Even with a switching LED, if I'm toggling with the PWM, I'd typically place a small decoupling capacitor close to the power and ground pins. Next, we have connectors, so various headers. I guess SSR might be solid state relay connectors, then we have fan connectors, serial wide debug, and UART. It's fine for these types of boards, but in general, I would want at least one ground pin adjacent to any signal pin. Here we just have one ground connection per connector, which is usually what people do, but ideally you want to account for return current as well, also when you're going through connectors. Let's move right. We have, I believe the STM32WB microcontroller has an integrated switch mode power supply, which is SMPS for short. Ideally, I would want this arranged differently, so all my grounds pointing down, all my decoupling capacitors vertical. But other than that, I think that looks okay. Again, sorry for the jumpiness. Now I'm jumping back to the power input section. So we have our power input header through this reverse polarity protection diode. So I would assume the input voltage is 5 volts, and that actually after the diode, we're going to have, of course, a diode voltage drop. So this isn't indicated as a Schottky diode. So if it's just a normal diode, this could be about 0.7 to 1 volt. So the voltage here might only be 4 volts. With a Schottky diode, it might be 4.7 or 4.5 volts. Now this becomes problematic because this AMS1117 LDO regulator, which steps your input voltage down to 3.3 volts, needs an input-output differential of, I believe, at least 1.2 volts. I would need to check the datasheet again. This is quite a common regulator. This diode might be problematic. If we have 5 volts here, yes, we're going to get 3.3 volts of the output. But if we have maybe 4 volts of the input, we're probably not going to get 3.3 volts of the output because of fairly high dropout voltage of this regulator. We also have some filtering in terms of ferrite beads and these capacitors. I would preferably also place a capacitor here and have a pi filter. I mean, for this design, it's not particularly important, but for commercial products, you want to minimize your conductor emissions. So you want your filter also to work in the opposite direction. So anything that is bled onto the power rail by your connected device should not be led out onto the cable, which can act as quite a good antenna. So I'd typically like to make these symmetrical, these filters. I assume the datasheet recommended 100 nanofarads in combination with this 10 microfarads, but usually, in a lot of cases, there's little to be gained. So I would just stick with the 10 microfarads, and you have to be careful with the AMS1117 as it can be unstable due to the low ESR of ceramic capacitors. Then we have a power on LED. Every time I do just ohms, not kilo ohms, I typically would want to add an R at the end just to really make sure, this is ohms, not kilo ohms. It's great that Lucas has labeled his nets, which is great. However, with this on LED, I would just add _K or _C to indicate that this pin is the cathode, because the anode is connected to 3.3 volts, and the negative side, so to speak, we indicate with the _K. Then we have our EEPROM, and Lucas has nicely remembered the pull-up resistors, and write protect is pertinently pulled low, and we have some sort of I2C address configuration, which he's written at 0x50, which is great, which helps him with his firmware later on and doesn't have to dig through the datasheet again. Then we have a buzzer and various MOSFETs powering relays and fans and so on. Okay, so for MOSFETs, I would typically also place a high-valued pull-down resistor on the gate just to make sure when the microcontroller is powering up, or generally if something might be going wrong, that the gate essentially is turned off, the transistor is turned off by pulling it low. I would place before the series gate resistor. So I'd do something, maybe like so, and then pull that to ground. This way, you don't form a potential divider, but you're still pulling the gate low. In any case, for all of these connections and even the buzzer, probably a piezoelectric buzzer, which can behave capacitively, most of these loads will be inductive. So a fan will be inductive, it will be some sort of motor, and we have relays which have coils. Now, anytime you try to disrupt current through a coil or inductor without any pathway to flow, you'll increase your voltage very rapidly and might be able to blow up these MOSFETs. Therefore, you always want these flyback diodes. So I'd always try and connect, let me just draw it very badly, kind of a flyback diode to power and the drain of my transistor, and I'll do this for all of these, including the buzzer, because the buzzer can, in some cases, behave inductively as well. So remember your flyback diodes. Okay, so we have another USB connector here, again ESD protection, which goes to the CH340, which is a USB to UART transceiver. Then we have a crystal, and I hope Lucas has calculated his load capacitances correctly and not just taken the values from the datasheet, because it's crystal dependent. Flipping TX and RX is oftentimes a problem as well, but I would assume I haven't checked the pinout of the STM32WB that this is correct. In any case, with TX and RX lines of UARTs, because they happen to be flipped very often, I usually place 0 ohm series resistors in the path in case something happens. Next, we have the microcontroller boot and oscillator section. So Lucas has the N reset pin connected to the switch below. Ideally, I would want this connection just to be on the right of the N reset pin, so it's more clear where this is connected to. Now, the STM32s typically have about a 40 kilo ohm pull-up resistor internally on the N reset line, so this R1 is pretty much optional, and C8 is useful to have as well, and a switch in case you want to reset the device. Now we have a high-speed crystal oscillator on OSC in and OSC out, which is at 32 MHz, which I hope is within the bounds of the STM32WB. A lot of the STM32 microcontrollers only accept up to about 24 MHz input frequency. And also, interestingly enough, he has set these capacitors as not fitted, so NF, which, unless there's a specific reason to, is wrong. Any crystal, unless the capacitance is integrated, will need external load capacitors, and this is dependent on the datasheet. If we look at the datasheet for this specific crystal, we can see it's just a crystal without any internal load capacitance, so these have to be fitted, these capacitors. For the low-speed external crystal, they seem to be fitted, however. He's also provided test points on HSE in and HSE out. And if you're not careful, and even with a 10x probe on an oscilloscope, the extra capacitance you are adding by probing the signal might stop oscillations or prevent oscillations from occurring. Now, STM32s actually have the option of outputting the master clock frequency on a separate pin, and that's a much better way of checking that your crystal is working correctly. Now for this reflow oven, you'll need some temperature measurement, and this is done via thermocouple, so he's using these SPI-based thermocouple interfaces, so basically ADCs, and this looks fine to me. Same SPI line, but 2 different chip selects as you would need. So coming close to the end of the schematic, we have the RF section, which is quite interesting. We have the RF connections of the STM32 microcontroller going through this IC here, and this IC happened to be a matching IC, specifically for the STM32WB line of microcontrollers. The RF connection on the microcontroller will have a certain complex impedance, and we want to match that typically to a 50 ohm antenna impedance. And this chip contains all the circuitry to do that, so that on the other side, you basically simply just have to connect this up to a 50 ohm antenna via 50 ohm trace. So it is good practice to include these, for example, pi filters over here, which are matching networks, and simply have a 0 Henry inductor or a short and not fitted capacitors in case you need to tune this matching network later. It's not 0R, it's of course 0H, because this is an inductor, not a resistor. Now, interestingly enough, I don't believe this is an active antenna. Well, if this isn't an active antenna and it's not being biased actively, so there's no bias T or any biasing output, I believe, on the RF out. That's why it makes you wonder why there are these blocking capacitors at C34 10 nanofarads. I checked datasheets and reference guides, and I believe this should just be a short, so I don't think there's any reason to have them there, and they could be harmful and could introduce loss into the signal. Something that's even more problematic is that Lucas is using an antenna, which is a PCB SMD antenna, but also in parallel has wired up an SMA connector going on a different path. We're at about 2.4 gigahertz, 2.5 gigahertz. He's just going to be using one of these antennas, and this will cause a problem because one on the other side will just be a long stub at these frequencies with additional components in the way. The way to do this is to have an RF switch which you can actively toggle to switch the paths, that this way you don't create stubs. This isn't great practice. So now we had a brief overview of the schematic, let's jump over to the PCB design. This is the PCB. It's a 4-layer PCB, so top and bottom are signal, and we'll have some planes internally. Let's just check the general layout quickly. So we have our microcontroller centered, regulator to the right of it. We have the antenna on the left, some various connectors at the top, buzzer, and on the bottom side we have USB connectors, other connectors and the reset switch and so on. Okay, so I would assume this will be partially mechanically constrained, so the mounting holes and connectors are probably fixed in position based on mechanical constraint. If not, I wouldn't put, for example, these connectors so close to each other. Once these are in, it might be hard to pull them out if they're so tightly spaced. Also, I wouldn't place these vertical connectors on the bottom unless there's a good reason to do so. If we also look at one of these USB connectors, the 3D model is for an SMD mount, but there's actually through-hole pins for this USB connector, so I'm not sure which model it actually is and which one is the right one. But again, let's go through, and sorry for the jumpiness, I'm just looking at things that kind of catch my eye. So first of all, let's look at the stack up. So layer 1 is front copper, filled in with ground. Then the first inner layer is ground. Second inner layer is VCC, which is at 3.3 volts. And the bottom layer is signals plus filled in with ground. So if you've been watching my channel for a bit, you know I prefer signal, ground, ground, signal for my 4-layer boards if I can get away with routing power, which in this case you can. Let me just hide the ground fill and let's look at the top layer. Let's examine the microcontroller first. So we have vias connecting the exposed pad of this QFN down to ground. And since this is a single-sided assembly, at least from the SMD components, it can be a bit challenging to lay out and route out a QFN package because we have very constrained space, so we can't put our decoupling capacitors as close as we want. So if we try and find our decoupling capacitors and where these need to connect into, we have some here connected via polygon pore, so that's already good. However, these ground vias are far too close to the pad. So they should preferably be moved out to prevent solder wicking, but more importantly, want to be considered about loop areas. So if you think of our power connection, 3.3 volts, then through to ground, through the ground via, ground plane, and up into this EP of this QFN. So we have a rather large loop area. So the question is, how can we decrease that? With single layer assembly, it's quite hard, but we can try and move the ground vias closer to the EP and then do the connections like so. In addition, it might be better to place the ground via up here and the 3.3 volt via close to it, because vias come in pairs and spacing them closely together as manufacturable and reasonable lowers your inductance, which can aid power delivery, especially since we're using a VCC plane. This via is also in pad, and that's not a good idea in general, so this should be moved out. There's also no reason why we can't make this via as small as, for example, this ground via over here. Again, I understand that it's difficult to route out a QFN package, especially with single-layered assembly, but there are certain things we can improve when it comes, for example, also to the layout of the crystals. For example, this LSE crystal up here, I typically like to lay out my crystals so the load capacitors are in the path of the crystal. This is rather crude, but something like this. So then I simply have to route from this crystal pad into the capacitor and into the crystal, and same on the other side, and I can tie my grounds together with a via connection to the ground plane. Same goes for the HSE crystal on the other side. Also, when routing out QFNs, I typically like to start with a fairly thin trace, of course not close to any manufacturing limits if I can, and then expand my trace width later if that's necessary. For example, this N reset line is at 0.254 millimeters, and you could route that out 0.15 millimeters to save yourself space, for example. If we move over to the bottom, remember this STM32WB has its own internal switch mode power supply, which requires external filtering in the form of an inductor, capacitors, and so on. I like the approach that Lucas has taken where he's routed out a pad and as soon as he can, widens that out. Ideally, I'd probably want to give myself a bit more space before I widen out, so I'd move that something like so, just to make sure I'm not causing any clearance constraints around this. In any case, you could probably improve this layout a bit. For example, if I move this inductor and place it like so, and then this capacitor like so, again, think about loop areas and keeping your distances as short as you can, especially when it comes to power. What Luke has also done with the crystal, this 32 megahertz crystal, he's created these long stubs for his test points, in addition to slightly suboptimal placement of the load capacitors. He's also chosen just to use the ground fill around the crystal to connect one pad, but the other one he's placed the via, so I'm not entirely sure for that reasoning. Also, the via again is right in the pad, which isn't great. So something like this might be better. The test points I would make smaller and put directly onto the traces that go into the crystal. This way you minimize stubs and you just provide yourself essentially a small solder mask opening for testing. Let's move over to this RF section. So we have the RF out pin on pin 21. This feeds into this matching network and through, again, a discrete matching network, which is probably not needed, into our SMD antenna. So as I know JLCs stack up and I know that 0.294 millimeters is a 50 ohm controlled impedance trace, so that's great. We want controlled impedance. However, Lucas has poured ground around the traces, in effect making this now a coplanar microstrip trace. which again changes the impedance. In this case, because you have more coupling to the ground around it, this will actually decrease the impedance. So you don't want to pour, unless you're creating a specific coplanar microstrip trace or strip line, you don't want to pour ground around your controlled impedance traces because that'll alter the impedance properties. We also want to keep our RF traces as short as possible. And here's the problem we saw in the schematic already. We're creating this branch, so we have 50 ohm branch going to the antenna 1 and another this RF 50 ohm branch going to this SMA or RF connector, which actually by the looks of it isn't an SMA, this is a UFL, so it's the wrong labeling as well. The problem is, assume we have 50 ohms on this line and then 50 ohms on this line, the actual impedance that this matching networks or this microcontroller sees is 50 ohm lines in parallel, so it'll see 25 ohms. Another problem is that we have this long stub here, which reacts capacitively and inductively depending on the configuration, but this will severely decrease your RF performance. Lucas did write that this Bluetooth at least worked, but I'm unsure how well and what data rates you can get through this. Also through this matching chip, you want vias again as close as possible to the IC and not rely on this copper pole to make your ground connection to the nearest ground via. So ground connection's right at the IC pretty much. The matching network is placed well because we are not creating any extra stubs. So a bad way of placing these matching networks might be like so, and then routing out to various matching components. Lucas did this completely right, that we want to route into the pads and minimize our stubs, at least on this line. Then we have our SMD antenna, and the layout requirements are given in the datasheet. It's this specific antenna, and all we have to do is follow the reference design. So we don't want any ground or copper poles around this area in white, and we want the trace spacings and widths and so forth. So essentially 50 ohms coming in, and again, this ground pole around it will change the impedance of this trace, so I would advise to get rid of that. But then as soon as we break into this area, we actually don't have a ground plane underneath, which again will change the impedance properties of this trace. So ideally, I'd probably want to expand this trace gradually, feeding into the pad width of this antenna, or simply follow what they've done in the reference design. Lucas also placed stitching vias outside the perimeter, which is certainly not harmful, but let's just check the spacing. So if we do inspect measure tool, we have a spacing of approximately 1 millimeter. So the spacing of your stitching vias can be determined quite easily. Essentially, you want them spaced at a maximum of the wavelength of your highest frequency of interest divided by 20. Now, since we're routing this as a microstrip, the propagation speed isn't simply the speed of light, it's the speed of light divided by the square root of the effective dielectric constant, which typically is 3.3. So to calculate our via stitching spacing, I take the speed of light, which is c, divide that by the square root of my effective dielectric constant for microstrip, which is about 3.3, so divide by the square root of 3.3, divide by my maximum frequency of interest, which is about 2.4 gigahertz, or 2.4 times 10 to the 9, and divide that whole number by 20, because we want our via spacing to be a 20th of the wavelength. I'm simply timesing by 10 to the 3 to get my result in millimeters, and ignoring the Google units, it's 3.4 millimeters spacing. So we could get away with actually keeping a via spacing that is something like this. So omitting these two vias like so. This is probably enough. Okay, so looking over this, I see over here is an EEPROM, and if you remember from the schematic, the EEPROM has pins A0, A1, A2, which are connected to ground, but they're not ground pins. They're simply there to tell the EEPROM which address it should present itself at, as on the I2C bus. So only pin 4 is ground, and pin 8 is VCC. Going back to the layout, pin 4 is our actual ground, and pin 8 is our VCC, and the way the decoupling capacitor is placed with this ground connection over here makes it seem like pin 7 is ground, which it isn't. Of course, these SOIC IC packages aren't the greatest for decoupling, but I preferably place the capacitor something like so, and then place my ground via right next to the capacitor like this. Remember, pin 7 is not an actual ground connection, it's an address select bit, but it's something that can easily catch you out. Again, vias are far too close to the pads, and also here, these vias are very close to this via over here. The via spacing is 0.1 millimeters, there's no reason for that. Also, Lucas, I assume, has thought to place ground vias closer to the signal via because it might be a transfer via because he's switching reference lanes. However, because he's using a signal ground power signal stack up, when you're switching layers, you're not switching from one ground reference to another ground reference, you're switching from a ground reference to a power reference, or from a power reference to a ground reference. Therefore, these transfer vias to help with the return paths won't do very much. What you want are essentially capacitors with vias close to your signal vias if you're doing this. And that's why I much prefer a signal ground signal stack up. We also have some USB traces, so one from the microcontroller going through the ESD protection into the USB-C connector. So first of all, this isn't the greatest design. There's no harm on these short scales, especially for USB full speed, just to route it. And this is very crudely done, even routing something like this, to me is more aesthetically pleasing, and you're not getting close to clearance constraints like you're doing, for example, on this side. So we have one part of the differential trace going here. Because it's USB-C, the cable of course can be flipped, so you'll have two differential pair connections, but this isn't the most elegant way of solving it. So we have this one long trace going into USB-D minus over here, but then on the other side we have USB-D plus just connected with a short trace. For USB full speed, you'll probably get away with this, but this is not good practice. Same thing with this other connector over here. Also, this intra-pair matching is not needed for full speed anyway, so I would just omit that, even though it looks cool. We also have this ground copper pole on the top and the bottom, and we have an internal ground layer, and I see there's some stitching vias missing, so we have stitching vias on the perimeter, but I'd also like to see stitching on the board center, so to speak, itself as well. And again, because of this USB differential traces, which should be impedance controlled, but this ground pole around it will change the impedance properties again, so this will throw off the impedance calculation. Then some further minor comments as well. The silkscreen isn't placed well. So we have silkscreen on components, on pads. We have silkscreen on holes underneath components with various stars instead of dots for pin 1 indicators, and so on. When we're looking at 3D models, we can also see they're not properly aligned for this connector. In comparison to all the other components on the board, this reset button is rather large. Again, maybe that's a mechanical thing. And we have a singular resistor SMD mount on the bottom side. So if you're doing single-sided assembly anyway, there's no harm in routing this further out from the buzzer and just on the same side. This doesn't have to be directly at the pins below, so you're suddenly making this into a 2-layer assembly board. So thanks again for watching this video. I hope it was useful and highlighting some aspects which could be improved on with this PCB design and also the schematic. There's more points I could make on this, but this video is probably already going to be quite long, so I hope at least that was helpful. So thanks again for watching, and I hope to review your designs in future videos. Thanks, and bye-bye.